Alright, so everyone, my name is Ritish. In this video, I am going to talk about order statistic filters or nonlinear filters and also about salt and pepper noise and how to reduce it. Order statistic filters are actually a type of smoothing spatial filters. So before we get into this, I'll explain in short what is spatial filtering and the types of spatial filters we have. Spatial filtering. Spatial domain in general refers to the image plane itself, which is the matrix that has pixel values of the image. For a grayscale image, this is a two-dimensional matrix, and for RGB image, this is three-dimensional. Spatial filtering is a type of spatial processing techniques, other being intensity transformation. Image processing techniques in this category are based on direct manipulation of the pixels in an image. In spatial filtering, we perform operations by working in the neighborhood of every pixel in an image. Whereas in intensity transformation, we operate on single pixel of an image. Some examples of spatial filtering techniques are image sharpening and smoothing. So what I mean by neighborhood is, consider this point x comma y here in the image plane. For this point, a 3 by 3 neighborhood is this part which is enclosed around this point x comma y. The neighborhood is now moved from pixel to pixel to generate output image. Now that you have some brief idea of what spatial processing is, let's look at what spatial filters are. Spatial filters. Spatial filters consist of two steps, a neighborhood as seen before and a predefined operation that is performed on the pixels inside this neighborhood. This is also referred to as spatial mask or window. Mask is usually added inside so that it has specific center pixel, and we match this center pixel with the pixel on our image on which we need to perform operation. So for our computational convenience, a square mask is used mostly. The mask is moved on the image such that the center of the mask traverses all the image pixels. The filtering operation creates a new pixel value replaced by the center pixel value in the mask. Later in this video, I'll explain how we perform operations inside this neighborhood and how we replace this. Now let's look at types of spatial filters. Spatial filters is classified into two types, smoothing spatial filters and sharpening spatial filters. Again, smoothing spatial filters is classified into two types, smoothing linear filters and smooth and non-linear filters or order statistic filters. Now our topic of interest in this video is this part. Smoothing spatial filters. Smoothing filters are used for blurring and for noise reduction. This removes high frequency component from the image such as noise and edges. For this reason, they are also known as low-pass filters, since they only let low frequencies pass through them. Blurring is used in pre-processing tasks such as removal of small details from an image prior to large object extraction. Noise reduction can be accomplished by blurring. Now that all the prerequisites are done, let's get into the main topic of this video, order statistic filters or nonlinear filters. Simply, these are nonlinear filters whose response is calculated based on ordering or ranking the pixels in the mask and then replacing the value of the center pixel in the mask with the value determined by the ranking result. In these filters, we change the order of the pixels to compute the end result. The order might be ascending order or descending order. As seen in the previous slide, order statistic filters are classified into three types. Median filter. In this, we replace the center pixel value with the median of the pixel values inside that neighborhood. In minimum filter, we replace this value with the minimum value of the pixel values, and in maximum filter, we replace this with the maximum value. Let's see an example on how we do all this. Consider an image with the pixel values as follows, which is this matrix here, and our pixel of interest is 27, which is this. Now, a 3 by 3 neighborhood matrix of this pixel 27 is this one. So, 3 rows and 3 columns. Now, the values of pixels in this 3 by 3 matrix are this. Arranging these values in ascending order, the order is this. Among these values, the middle value is 25. So, applying median filter, The resultant image is this. So we change the pixel value with 27 to 25. Mathematical expression for median filter is this one. And among the values, the minimum value is 18. So applying minimum filter, the resultant image is this. In the same way, the maximum value is 97. So applying maximum filter, the resultant image is this. So in this way, we apply the processing or the operation on every pixel inside this image to get the resultant image. Let's see some applications of order statistic filters. Median filters are quite popular because for certain types of random noise, they provide excellent noise reduction capabilities with less blurring than linear smoothing filters. Median filters are particularly effective in the presence of impulsive noise, also called salt and pepper noise, because of its appearance as black and white dots on the image. Maximum filters are useful in finding the bright spots in an image, also called pepper noise. Similarly, minimum filters are used to reduce salt noise. Now let's get into the second main topic of this video. What is salt and pepper noise? Salt and pepper noise is an impulsive type of noise in images. We consider salt and pepper noise for which a certain amount of pixels in the image are either black or white. That means black or white dots. Normally, if there are black dots in the image, we call it as pepper noise. And if there are white dots in the image, we call it as salt noise. This noise is generally caused by errors in data transmission, failure in memory cell, or analog to digital converter errors. So these are some examples of images encoded with salt and pepper noise. So salt noise means white spots like this, and pepper noise have dark spots like this. An image with both salt and pepper noise, that is white and black dots, looks like this. Removing salt and pepper noise. Consider this image with salt and pepper noise imposed on it. First, let's consider an averaging mask. For this image, after passing it through 3 by 3 averaging mask, the image looks like this. As we can see, there isn't much change in the image and we can't extract much information from this. Now, if we use a median filter on the same image, it looks like this. We can observe that the image now is much smooth and clear from noise. Imagine this and the previous slides are taken from the book Digital Image Processing by Rafael C. Gonzalez. So, for now we are done with the theory part. Let's look at the Matlab code to implement this practically. First, let's consider a grayscale image. So this is the Matlab code. First I will loaded the image gray.jpg into a variable original image. So let me just show you the image. Yeah, so this is the image. Later I added salt and pepper noise with the inbuilt im noise function and described the noise to be salt and pepper. And I have added 15% noise to the image. So after adding the noise, the image now looks like this. Yeah. So this is the image with added noise, with added salt and pepper noise. To remove this noise, I have used the inbuilt medium filter function in Matlab, medfill2. And in here, I have specified the neighborhood of each pixel to be 3 cross 3. So after filtering, the image now looks like this. Yeah, so you can see that the noise is mostly reduced, other than we have just some white and black spots in the image. Comparing the image before filtering and after filtering, it looks like this. So we can see that the noisy image is this, which is full of which is not clear, and this is the filter image, which is very smooth and very clear, so that we can extract some information from this. Now that we have seen how to reduce salt and pepper noise, let's see what happens when we increase this noise percentage. For this now, I have loaded the same image used previously into the original image variable using the imDate function, and I have created three noisy images now with 10% noise, 20% noise, and 30% noise, and use medium filter function on three of the images. And after plotting all these images before filtering and after filtering, it looks like this. Yep, so as you can see, these are the noisy images with 10% noise, 20% noise, 30% noise. The noise is increasing as we go downwards, and after filtering we can see the net resultant images. This image is much more clear when compared to this. So we can say from this that as the noise increases, even medium filter isn't that much efficient. In order to increase efficiency of this filter, we increase the neighborhood of the pixel to get the resultant image much close to the true image. So let's see how this happens. So to see the effect of the size of neighborhood in median filter, this is the code in which I have used the same create.jpg image and loaded into the variable using the imRate function, and I have added 30% salt and pepper noise with the imNoise function. Now I have used the median filter function 2 times on the same image with 3 by 3 neighborhood matrix on once and 5 by 5 neighborhood matrix twice. So to see the net result, I'll just show it now. So here we can see the original image, and this is a noisy image with 30% noise, and these are the filter images with 3 by 3 neighborhood matrix and 5 by 5 neighborhood. Notice that the 5 by 5 neighborhood, after filtering using the 5 by 5 neighborhood matrix, the image is much clearer and much smooth when compared to this image. So in this way we can increase the efficiency of median filter by increasing the size of neighborhood matrix. Now that we have seen how to remove salt and pepper noise from a grayscale image, let's see how we can do the same on an RGB image. So this is the Matlab code. This is the RGB image that I'm using, and I have loaded this image into the variable I. Notice that I is a 3-dimensional matrix here, 540 cross 960 cross 3. Let me show you the image. Yep, so this is the original image. Now to this I have added 20% salt and pepper noise using the same imNoise function. So the image after adding noise looks like this. So this is the image with 20% noise. So the thing is, now we are splitting the RGB image into 3 parts. One is the red channel, green channel, and the blue channel. Since the inbuilt median filter function in Matlab can be applied only for 2-dimensional matrices. So from this noisy image, notice that even here the noisy image now too is a 3-dimensional matrix, 540 cross 960 cross 3 over here. So from this RGB image, I'm extracting the first layer and assigning it to the variable red channel. Similarly, I'm extracting only the second layer and assigning it to green channel, and the third layer to blue channel. And later applying median filter with 3 by 3 neighborhood matrix on each of these channels, and the filtered channels are assigned to these variables. Since we have taken RGB image, so I'm concatenating all these 3 channels to get the final net resultant image. So concatenating all these 3 using the cat function, and I'm assigning the final RGB image to this variable final image. So the net resultant image after filtering using median filter looks like this. Yep. So this is the image. We can see that the noise is very much reduced. Comparing them side by side, it looks like this. Yep, as we can see here, this is the noise image which is not much clear and smooth, and this is the filtered image uh, that is very clear and smooth, so that we can know what is actually there in the image. We can extract some information from that. And the drive links for all these Matlab .m files of these codes are attached in the description of this video. Do check it out. Let's summarize what we have discussed in this video. First, we have seen about spatial filtering, spatial filters, and the types of spatial filters. In that, we have briefly seen about what are smoothing spatial filters, and then we jumped into the main part of this video, order statistic filters, and we have discussed about it with an example. Later, we have seen about applications of order statistic filters. Next, we entered into the second part of this video, where we have discussed about what is salt and pepper noise and the Matlab code for removing salt and pepper noise. These are the references I have followed for this video. One is the book Digital Image Processing by Rafael C. Gonzalez and Richard E. Woods. Another is an article on removal of salt and pepper noise with median filtering by Pravir Jainati. And this is the link for this article. Also, I have attached this link in the description of this video. Do check it out. If you have any queries, feel free to post them in the comment section. Thank you.